Good.
Morning. Have you had a good weekend? Happy back?
No.
Good. Okay, so we're looking at stabilisation of radicals, and we talked about hyperconjugation, which is also with alkyl radical stability, and we've been talking about resonance. And the last particularly interesting one, I think, is what's called the cathode-dative effect. So, when you've got an electron withdrawing group and a donating group, both present adjacent to the radical site, you get extra stabilisation. It's known as cathode-dative stabilisation, and it's greater than the sum of the two stabilising effects. So it's a synergistic effect. Synergistic. So the stabilisation by the donor plus the stabilisation by the acceptor is less than the actual observed stabilisation. So let's have a look at an example. That compound there, that radical, is a cathode-datively stabilised radical. The stabilisation energy, which we discussed last time, is 130 kilojoules per mole. So the amino group is what we call the donor. And the carbonyl is the acceptor. Okay, so we look at the individual effects of just the donor on an amino methyl radical. The stability, extra stability of a methyl is 42 kJ per mole. So the donor only improves stability by 42, and the acceptor only improves stability by 54. If you do the linear sum of those, of course, you get to 96, which is a lot less than the observed stability of 130. So we get 34 kilojoules per mole extra stability due to the synergism. So these particular radicals are often the most stable ones we find of simple radical types. So the acceptor, the aldehyde, stabilises the radical, or the orbital, the SOMO, and allows it to interact more readily, readily with the donor. So essentially you lower the energy of the SOMO so that the donor can interact with it better. And there's a classic example of one such radical which you can actually distill. So that's the cathode-dative part of this distillable radical. It also has a ring system around it, which is resonance stabilising. So here is our donor, and here is our acceptor, interacting to stabilise that radical synergistically. Of course, we've also got extra resonance as well. So that's actually a distillable radical, so you wouldn't call that a particularly reactive intermediate. It's a nice stable radical. So these are all what we call thermodynamic effects. We're talking about thermodynamic stabilising effects, resonance, hyperconjugation, and this cathode-dative effect. The other sort of stability is kinetic stability, which is just the fact they react slowly. So in certain cases, radicals appear to be more stable than their bond dissociation energies would lead you to believe. And that's because they are kinetically stable. as in they react slowly. And the main reason for them to react slowly is simply down to sterics. So there on the left is a phenyl radical. A phenyl radical is a very reactive radical usually. The stabilisation energy is negative, it's less stable than methyl, but that one does not react for a half-life of 0.1 seconds. And that's purely because of the steric congestion of those two big tertiary butyl groups. The one on the right does have hyperconjugative stabilisation, but again it's got big butyl groups surrounding it, and the half-life of that is 20 minutes. That's a substantial half-life for a radical. These things do still react with oxygen. You have to keep clear of oxygen. The reason for that is oxygen, as we know, is a diradical, and it's small and it's linear, so it tends to get in regardless of steric congestion. Okay, so that last sheet's really been about the different sorts of stability we can have of radicals in terms of thermodynamics and kinetics. We're now going to move on to the history of radical chemistry before moving on to modern day applications. So some of this you'll have seen before, and some you won't. Has everyone got a handout? Anyone not got a handout? Right. So, the first one we're going to look at is what's known as Gomberg's radical. So I gave you a question, or 3 questions last time. I'm going to answer the third one with the next few slides. So Gomberg is was sort of originator of all radical chemistry. He was around in the 1900s, late 1800s, and he understood or thought that radicals did exist, but wasn't sure. And he's looked upon as being the father of radical chemistry. So what he started off by doing was he took something that was available in those days, triphenyl chloromethane in benzene, don't do that anymore, it's toxic, and he used metallic silver, which we don't anymore because it's expensive, and he heated them all together, and what he found was that the solution went yellow, and as he evaporated off the solvents he got a dimeric compound. So what he was doing is taking triphenyl chloromethane with silver, and he's heating it in benzene. And it went in dilute solution, it went yellow because he's making the triphenyl methyl radical and silver chloride. We'll come back to that in a minute. And of course in those days he hadn't got NMRs or anything else to swap with, and he assumed that as he evaporated off the solvents and increased the concentration, these then combined to give him hexaphenyl ethane. Which is that, just direct combination of 2 of those radicals. Question mark. That of course is C38H30, you knew that much. And of course in 1900 you wouldn't have thought anything different than that being the possibility. So this is an example of a radical generation via transfer of an electron from a redox active metal, silver. So let's just think about how radicals form to start with. You take triphenyl chloromethane, silver, might be silver 1, so it's happy to give us an electron. two aromatic rings in our starting material, so we can give our starting material an electron, and we'll come back again to more detail of that in a second. Okay, dot minus, radical anion, giving our starting material an electron, radical anion. And that radical anion can then lose chloride, and of course that will give us silver chloride, and also generate a radical, triphenyl methyl. So it's give an electron, then lose chloride, then lose an anion. That of course becomes silver chloride. So that's how the radical is generated. Now, if you think about your respective products, hexaphenyl A-plane, anybody want to tell me what the NMR spectrum would look like? Would it look very interesting? Second?
No.
No? Good. What does it look like? Where do those signals be? Where the aromatic hydrogens appear in the NMR spectrum?
6 to 8.
Thank you. We'd expect to see 30 hydrogens between 6.5 to 7.5. Very boring spectrum. ppm. Of course, Stomberg in 1900 hadn't got the benefit of an NMR machine, so he thought he'd made this dynamo. Okay, so with the advent of NMR, it's appeared that this is no longer the correct structure. So let's just see what the actual NMR data. The actual NMR data was acquired in 1968. And if you look on Blackboard, you can see the original paper. So the NMR data for the dimer is as follows. Delta H, 6.8 to 7.4, 25 H multiplet, not 30. 5.8 to 6.4, 4H multiplet. 5.0, 1H triplet. So we've got what appear to be three different environments for the hydrogens in our dimer, unlike the proposed structure. Bless you. So, why? First of all, the triphenyl methyl radical isn't as stable as you might think in terms of its bond dissociation energy. Let's look at the stabilization energy of phenyl CH2 dot. That's a carbon with one phenyl ring attached to it. That is 83 kilojoules per mole more stable than methyl. Triphenyl methyl, you might logically think to be 3 times as stable as that, but it's not. Triphenyl methyl radical is 117 kilojoules per mole more stable than methyl. So it's not as stable as you predict for the summative effects of 3 phenyl rings, and that's because it's not flat. Phenyl rings of triphenyl methyl are actually like a 3-bladed propeller rather than being flat, which means that we don't get very effective delocalization. If you look at your radical centre there, if it was flat, that would very happily resonate all the way through those 3 phenyl rings, and you'd expect it to be a lot more stable than it appears to be. The problem with that structure is that the hydrogens, orthohydrogens on the benzene rings, bash into each other. They are almost touching. and that's an unfavourable effect. So we lose a little bit of conjugation. I can still conjugate, but not as effectively, because the female rings twist slightly into a propeller shape, which takes the hydrogens away from each other, but we no longer have a completely flat system. There's still overlap, some overlap, but it's not as good as it would have been if it's completely flat. So delocalization is not as efficient as you might have thought for a completely flat structure, which leads to this observation of not as much stabilization as what should be. Right, so the central carbon of that twisted structure, of course, is quite hindered. Along the flat, it's got steric constraints around it, so it's not as accessible as the completely flat radical would be. So the central carbon is severely sterically congested and not very accessible, so kinetically fairly slow to react. So dimerization via two of those central radicals isn't likely to happen. And consequently we get an unsymmetrical dimer rather than a symmetrical one. Right, so triphenyl methyl is a propeller. Just to show you, if you can all see this, there is triphenyl methyl, and you can see the hydrogens, orthohydrogens, are right next to each other. That is not a happy structure, and it's not surprising that we twist out of plane state hydrogens away from each other. So it does that with all three of them, and we get a propeller shape. Right, so what's actually happening in this reaction? So we met the Birch reduction last time. That was a sodium reduction of an aromatic. Let's look at the corresponding thing with triphenyl chloromethane and silver. Right, so there's triphenyl chloromethane. Silver wants to give an electron. That's fine. Ag goes to Ag plus E minus. Aromatic rings like to accept electrons, or can do. So let's give that electron to our aromatic ring, like we did with the Birch reduction, and that generates a radical anion forming. Dot minus. All sorts of resonance forms for that structure. We know from what I drew before that we generate chloride. Well, that particular resonance form is very useful for generating chloride. I can take that negative charge and I can expel Cl minus. So there we are, there's a single electron donation followed by loss of chloride. And that is triphenyl methyl radical, one resonance form thereof. Of course, there are two other resonance forms of that species. There's the one we predict to be the most likely, where the radical is on the central carbon. As so. And there's also one where it can be on the para carbon of the aromatic ring, or Bond's aromatic ring. So these are the three resonance forms of the triphenyl methyl radical. The most dominant one will be this one. because it maintains the aromaticity of the benzene rings, but it's hindered. And the most accessible one, of course, is that one. So we've got a higher concentration or a higher proportion of the resonance on the left. We've got access to on the right. And those are the two that combine. One molecule reacts via the central carbon and one molecule reacts via the terminal carbon. To give us an unsymmetrical dimer. That is in fact Gomberg's dimer, and the NMR data fits perfectly. We've got 25 aromatic hydrogens. Which is what we had in the NMR data. We've got 4 alkene hydrogens. 1, 2, 3, and 4. And the other ones at 5.8, 6.4. And the one that people tend to forget about, of course, there's still a hydrogen stuck in the middle here. And that's the one that appears at 5.0, 1H triplet. So, Gomberg was a very clever man. He hadn't got the access to the data that we have these days. And that is the first radical reaction to have been carried out in anger, as it were, in terms of trying to find out or prove the existence of this carbon with 7 electrons around it. Okay, so that's back in 1900. Moving forward a few years, we come to free radical halogenation, and again, it's a very, very important method for the functionalisation of hydrocarbons. We can't functionalise hydrocarbons at all easily without using radical reactions, and this is our first example of a chain reaction. Nearly all synthetically useful reactions of radicals are chain reactions. And this is the first one that we'll meet, and it's classic. We have an initiation event, we have propagation steps, and we have infrequent termination steps. So usually we're using bromine or chlorine. Which I shall depict as X2. Both of those have got fairly weak bonds. So we have XX, and the initiation event is either thermally or photochemically we break the XX bond. Either heat or UV light. We split that bond in a fraction of the molecules that are present at X2. So we only generate a very tiny amount of X dot, Br dot, Cl dot. Trace amount. We don't want large concentrations of radicals as we get dimers. Trace. Okay, just so you are aware, bond dissociation energy of bromine is 192 kilojoules per mole, and chlorine is 253. So those are both relatively weak bonds which we can cleave photochemically or thermally. That Out of interest, is the iodine bond stronger or weaker than bromine? Come on, you're better inorganic chemist than me. I2, is the iodine bond weak or strong compared to bromine? Weaker. Good. Very weak. 151. You want to speculate how strong the fluorine-fluorine bond is? It going to be strong?
No.
Why
Paul
not?
and Patrick pal each other.
Brilliant.
Boom.
Thank you. Anyone want to suggest what the bond association energy is? Boom. 155. It's not the same as iodine. I think it's quite surprising. It's not quite boom, is it? Okay, propagation. So we've got Cl dot or Br dot, and we can now react with our alkane and abstract hydrogen atom. So these are what's called the propagation steps. Make sure you're using your single-headed arrows. Extract the hydrogen from that alkane to give us R dot and HX. Trace amount of R dot. Please don't forget we're dealing with small quantities. Trace. Otherwise you get diamonds. R dot then reacts with the abundance of X2 we've got left. We only split a little bit of it. Abstract X. That gives us our desired product. And it regenerates our halogen radical. And that is what we call the chain carrier. We've got a trace amount of it, reactive, we can go back and rejoin the cycle. So that's our little chain cycle of events, which are the propagation sequence. We want that to be a good sequence with a long lifetime for a successful reaction. Hence, you only want trace amounts of radical at any one time. Any reaction that destroys radical character kills the reaction. And that's what happens when we terminate the reaction. If we have two radicals reacting together, we remove radical species, so the chain stops. So very occasionally, two radicals collide, we generate something that's not a radical, and that breaks the chain. This is a very uncommon reaction because our concentration of radicals is so low. However, if they do happen to bump into each other, the rate is very large. So it's a very fast reaction in terms of rate constant. And the various termination steps, obviously we can generate two alkyls combined, we can regenerate our halogen, or we can make some product. But all of those kill the radical character and will stop the chain from carrying on. Undesired. That's the classic chain reaction. Almost every reaction we'll look at, bar two, are chain reactions. So when it comes to looking at exam questions, we're generally looking at chain reactions. We can characterise a chain length, which is how many propagation steps occur per initiation event, and we want that chain length to be as good or as big as possible for a successful radical reaction. That's the classic free radical halogenation of alkanes. Really useful. You can't functionalise propane, butane, pentane, hexane without using radical type chemistry. Right. So, the problem with this reaction, of course, is that not all hydrogens in alkanes are the same. apart from methane and ethane, we've got all sorts of different hydrogens, in and out alkanes, and we have to think about which product we're going to get, or find out which product we're going to get under given conditions. And again, a very important point here is the rate limiting step, the one that controls the product and the rate, is the abstraction of hydrogen by the halogen radical. Once you've done the abstraction, the product is determined. So there's 2-methyl propane. We've got a primary hydrogen and a tertiary hydrogen. X dot to abstract primary. To give us a primary alkyl radical. So that's primary abstraction. That then reacts with X2 to give us a primary alkyl halide. Okay, but equally we could, of course, abstract the tertiary one, going green, which gives us a tertiary alkyl radical. Which then reacts with X2 to give us tertiary alkyl halide. Now, if it was doing this completely randomly, then of course this sort of reaction would be fairly useless to us, because we get a dog to dinner of a mixture of products. Happily, the product distribution can be controlled depending on what halogen we use. So if we actually use bromine or chlorine, we get a different product distribution. So there's our tertiary, and there's our primary. That's using bromine, that's using chlorine. Bromine gives us almost exclusively one product. Greater than 99%, less than 1%. So free radical bromination is very selective. Chlorination is fairly useless on this particular reaction. About 40% to about 60%. So we get not far off a 1-to-1 mixture. So, and that's all down to which hydrogen we abstract with either Br dot or Cl dot. So Br dot clearly abstracts selectively, Cl dot doesn't. Cl dot is much more reactive than Br dot, and as I said in lecture 1, it's like a building in a china shop, it takes whichever one it wants to. So Cl dot doesn't really distinguish between the various hydrogens in our starting material, and we get a mixture of products. And there's a nice question in my latest question set which will make you think about that a bit more. Right. So Gomberg. Halogenation. People tend to overlook halogenation of alkanes. It's really, really useful. Once you've got a haloalkane, you can do all sorts of chemistry with it. Okay, so HBr to alkenes. Year 1, semester 2, or even semester 1, you met a rule named after a chap called Markovnikov. So when we're doing electrophilic addition of HX to an alkene, we get one particular product. And what his rule says is in the addition of HX to an alkene, that's the electrophilic addition, of HX to an alkene, the more highly substituted carbeniamine or carbocation is formed in preference to the less highly substituted one. H plus, you can't see, it's hold the bottom. Good. Reacts with alkene, preferentially to give us a tertiary carbocation, which reacts with chloride. To give us the tertiary alkane. It does not react in the other direction. To give us the primary cation, and then the primary alkyl halide. That being because, of course, tertiary cations are more stable than primary, and that's the rate limiting step, the formation of that role. It's therefore much faster. Lots of gesundheit, everyone, by the way. Right. Now, in the 1920s, so we've moved on a bit from Gomberg, some researchers found they started to get mixtures of products from doing these reactions, so they're starting to doubt what McCuffin said. So they're adding HBr to alkenes such as allyl bromide, and they're finding mixtures, random mixtures it seemed, of Markovnikov products and so-called anti-Markovnikov products. So they're getting, that'll be the Markovnikov product. And that'll be the anti-Markovnikov product. And it was indiscriminate, so they're getting random mixtures of the two. And they start to think, well, what's going on? Why is our reactions not doing what Vladimir told us they should do? And what they found was that it was down to the presence of peroxides. ROOR. And the presence of these peroxides results in competing reactions of radical nature. Now the OO bond is weak. Is it a boom weakness, or is it less than boom? Where's my boom person? It's actually weaker than the fluorine bond. The OO bond is 146 kilojoules per mole. That's a weak bond. Okay, so it rapidly cleaves under fairly weakly thermal conditions. And this gives alkoxy radicals, which then initiates a radical addition of HBr to alkenes instead of electrophilic reaction. And this reaction was probably the first one to be put on a firm mechanistic basis. And again, it's a chain reaction. So it starts off with some peroxide with its weak bond. They do go boom, actually, if you heat them very nastily. And that will homolyse to give us two alkoxy radicals. HBr is a relatively weak bond in it. Got a trace amount of O dot trace. The OH bond is very strong. We met that before. So an alkoxy radical will very rapidly abstract the hydrogen from HBr to make a nice strong OH bond and Br dot trace. And remember from the first lecture I said radical reactions all involve either abstraction or addition. Well, that's abstraction. And that's that's our initiation process. The propagation process is addition. We'll use the example we've done before. So we now add the alkene, and radical addition to alkenes of that sort almost always gives you the more stable secondary radical. We've got a radical, we've still got HBr present, it's a relatively weak bond. Strong is a lot stronger. So we abstract a hydrogen and HBr, keeps our product, and our chain carrier, Br dot. And round we go again, chain carrier. Chain reaction, 2 repeating steps, addition followed by abstraction. So that point I made last time was shown here very clearly. The major reactions of radicals are addition or abstraction. And in regiochemistry, which end the bromine reacts to, is determined by what we call step 3, and we generate the more stable radical in the addition step and form the intermediate. Right, I want to stop there in terms of the lecture. I want to look at the questions I gave you out last time, which we've covered one of. So, I think we've all got this. And these are all for your own benefit for revision purposes, really. So the third question I gave you was basically the Gomberg question, which we've now covered. So we've gone through all this. We now know why the NMR data for his dimer is shown at the bottom. The first question is, what is the reactive intermediate? I'll give some details of the different types. That is bookwork, which I don't really need to go through. It's our first lecture, first 3 pages. So that involves drawing reaction profiles to show a high energy intermediate, and talking about radicals, carbene, enzymes, such like. Perhaps the most relevant one to what we discussed today is the second one. And I said, rank the carbon radicals 1 to 5 in order of increasing stability. So, I'm sure you've all done it. Yes? No? Which one's the least stable of those radicals?
Number 2.
Number 2. Good. Least. Why? Anybody? Okay, the phenyl radical is hot. And the reason is that radical cannot delocalize. People often tell me that it can, it can't. So the phenyl radical, there's our benzene ring, 6 pi electrons. The phenyl radical is orthogonal to the pi system, not delocalized. There is no stabilization of that single electron. Right, that is why it's hot, very reactive. Stabilization energy of the phenyl radical is minus 25 kilojoules per mole. Right, anybody know what the second least stable one is? 1, good. Then 1, so it's 2, then 1. And what's the stabilizing effect on number 1? Why is 2-propyl radical more stable than methyl? Hyperconjugation, thank you. Hyperconjugation. Which is the overlap between the CH sigma bond and the singly occupied orbital. Anybody want to suggest what the third one is?
Number 4.
Number 4, brilliant. The minor methyl. That's got a stabilisation energy of around 42 kilojoules per mole. And that's because there's a resonance, which we drew last time, which is more powerful than hyperconjugation, where you take one electron from the nitrogen and pair it up with a single electron. Do look back at your notes, because people often get that resonance misconstrued into dipole resonance. Stronger than hyperconjugation, but not as strong as some other things. Okay, what about the fourth one?
Third one? It's number 5.
This is number 5, they're close. Okay, number 5 is triphenyl methyl, which, as we just met, is not that flat. So it's not as stable as you might think it is. So it is highly conjugated, but not as much as we thought it should be, because it's got a propeller shape. Highly conjugated, but twisted. And number 3 we met just before, has a stabilisation of 130 kilojoules per mole. That is the most stable one we've got there, due to the capsule-dated effect. Okay, so we call it a day there.